Hello everyone, and welcome to the Solar School side event in the frame of SolarPACES 2021. My name is Konstantinos Gennikomsakis and I'm an EU Projects Officer at Estella, the European Association promoting solar thermal electricity in Europe and the MENA countries. Today, Solar School Consortium partners from both concentrated solar power and supercritical carbon dioxide turbomachinery sectors will give you answers on how an innovative sCO2 CSP plant design can be a game changer for decarbonizing our energy system towards a zero pollution future. Our event will start with a presentation from Arena Consulting to introduce you to the Solar School project. Then we will have a joint presentation on Solar School demo site plans and future hybrid systems by KTH, Abengoa and Magtel. Then we will have a presentation on the advancements on the supercritical carbon dioxide cycle and turbomachinery by the University of Genoa, Baker Hughes and Franco Tossi Meccanica. It will follow a presentation of the advancements on the heat exchangers and molten salt electric heaters by Lointec and Seiko. Before we kickstart our event, I would like to remind you that there is also a Q&A section at the bottom of your screen. If you have any questions, please write it here and we will have the last 20 minutes devoted to answering your questions. Now I would like to give the floor to Stefano Barberis from Arena Consulting, who is the project coordinator, to give you an introduction of the Solar School project. Stefano, please share your screen.
Good evening, everybody, first of all, and I hope you can see my screen. Thanks, Konstantinos, for this kind introduction. My name is Stefano Barberis from Arena Consulting, and I am Solar School Project Coordinator. Solar School Project Coordinator is the first European funded project who's dedicated completely to coupling CSP and supercritical CO2. Why this? Because supercritical CO2 cycles are compact and could have a strong potential in terms of cost reduction for CSP power cycles, and at the same time, because supercritical CO2 cycles can operate and have nice efficiency, particularly in the temperature range that is currently covered by CSP power plants, not only high temperature ones, so not only solar tower ones, but even parabolic trough. So supercritical CO2 could be a very relevant technology to be coupled with concentrating solar power in order to make concentrating solar power more flexible, more cost effective, and also more compact without the use of water that, as we all know, is is always a challenge in desert areas or high irradiated areas that are crucial and relevant for CSP. What are the challenges? The fact is that so far, supercritical CO2 cycles are quite immature, and there have not been so many demonstrations, particularly here in Europe. There are several R&D projects, but there is no demonstration so far for what it concerns megawatt scale. And at the same time, there are some new projects in the US, for example, like the STEP project that is working on demonstration of supercritical CO2 at a temperature around 700 degrees. This is the fact that, these are exactly the temperature where, for example, molten salt system coupled with an electric heater that can boost the temperature of our solar field collection can operate. So in that sense, in Solar School project, we tried to tackle all the challenges that I mentioned before, and also think about how to achieve these 700 degrees, 650, 600 degrees Celsius that are exactly the best operating temperature for supercritical CO2 coupling CSP and PV. And how to do that? How to do this? Thanks to a proper coupling of PV, electric heater, and molten salt storage tank. This is something that we will see also more in detail during the presentation by Lointec and Seiko about the fact that not only the supercritical CO2 turbomachinery will be protagonists in our project, but also the electric heater as key enabling technologies for this coupling between CSP and PV in order to make them, let's say, friend in the energy market. So what is SolarSchool? SolarSchool is a European funded project, 4 years long. We started the project last year in October, and we have just, let's say, we are just celebrating the first birthday of our project, whose goal is to realize the first megawatt scale demonstration of how to couple CSP and supercritical CO2 in order to make CSP projects, CSP power plants more flexible, less dependent to water due to the fact that we will not use steam for sure. We will not be based on Rankine cycle, but we will be based on coupling Brayton cycle with CSP. But let's say not traditional air Brayton cycle that require very high temperature, but supercritical CO2 Brayton cycle. In this way, the goal of the project is to strengthen from one side the CSP sector, the European CSP industry, and from another side, the European turbomachinery industry. The goal of the project, as I said, is to make a hybrid PV plus a molten salt-based CSP plant towards a very grid flexible supercritical CO2 power plant. Why very grid flexible? Because thanks to the use of electric heater and coupling it with the molten salt tank, we will be able to harness as much as we can the potentialities from PV plants, and also at the same time to operate ancillary services, for example, both in production, thanks to a more flexible power cycle as the supercritical CO2 Brayton one is, coupled with the molten storage tank, but at the same time also acquiring electricity from the grid when required, producing heat via the electric heater, and storing this heat via a thermal battery that will be the molten storage tank. In this way, we will be able to operate the supercritical CO2 always at its best efficiency and with a number of operating hours as high as possible. As I already said, the idea is to demonstrate for the first time a megawatt scale supercritical CO2 cycle, not only, let's say, megawatt scale. For the supercritical CO2 cycle is the first of its kind megawatt scale in Europe, but for sure the first of its kind operating coupled with CSP. To do so, we will perform a demonstration in La Africana plant, a power plant managed by Magdal, which is one of our project partners, where we will realize a dedicated molten storage buffer tank, and where we will study the potential hybridization, as I said, with PV, also thanks to the use of this electric heater. So we will operate in a real field, in a real solar field, with a dedicated molten salt tank that will be coupled to our supercritical CO2 power plant at the end of the day, a real TRL7 demonstration. Our objective is therefore to develop all the technologies and all the components that will be needed to realize and operate such a power cycle, from turbomachinery to electric heaters, heat exchanger, etc. And to do so, we engaged partners from all over Europe under the coordination of Rina Consulting, having also the chance to study the replication of SolarSchool power plant, not only Europe, but even in Morocco, with the engagement of Mazen. So, as you can see, this is a very industry-driven consortium with both big turbomachinery operator involved, like Baker Hughes and Franco Tosi, that will present later on their activities, as well as key CSP players like Arevoa, and also heat exchanger and electric heater manufacturer like SiCo and Lointec. All these industrial partners are supported by relevant CSP R&D partners like University of Geneva, KTH, who is the scientific coordinator of the project, CERT, Ikerlan, and also with the perfect coordination from Estela as the European Association of CSP stakeholders to support the replication and the promotion of project results. As I said, the goal of the project is to make a first demonstration, also in order to launch on the market the supercritical CO2 turbo machinery as a whole, so not only for CSP application, within 2030. So the strong presence of industrial partners in the project guarantee a real demonstration to market orientation of the project. If you would like to support us, first of all, let me thank you to be here today to, let's say, get some know-how about our project, but please visit our website, www.solarschool.eu, and try and become part of our stakeholders group, because all our activities are, let's say, corroborated by your feedback, and all our R&D activities will be stronger and more efficient and more effective thanks to your insights. So please take a look to our website, take a look to our social media, and if you have any question, do not hesitate to ask us even today or during the next days, thanks to our website. I leave now the word to the rest of the panelists, who will provide you more and more hints and more focus on the technology to be developed in the project.
Stefano, thank you very much for this very interesting introduction to the concept of the project, its objectives and goals. I would like to ask you to stop sharing your screen so that the next speaker, Rafael Guedes from KTH, can give his presentation about the solar school layouts. Rafael, the floor is yours.
Okay, thank you, Constantino. Sorry, I was on meeting. Good evening, everyone in Europe, or good morning, afternoon, if you are in America or Australia. So I will just build up on what Stefano was presenting, and I'll move on more into the technical activities we've been carrying in the first year of the project. And especially I give up motivation to, building up on what Stefano said. Why are we looking particularly into this combination, hybridization using molten salts? And then how do we see it beyond? So this work, here it's not only from a KTH side, but also from Abengoa and Mactel, which are leading the engineering efforts to what concerns the demonstration plan. So this already was mentioned by Stefano, but I think our main driver or motivation to do this is to combine two things. So on one hand, that we foresee that to reach more cost competitiveness in CSP, we need to reach higher temperatures and so forth, but yet the solar collector side is yet to be demonstrated. So at the same time, the power cycle that could enable such temperatures, systems at high temperatures like the supercritical CO2, is also immature and needs to be demonstrated. So we thought, okay, when foreseeing this project is on both sides are immature, you could say, so the power block and the solar collector side. So our approach was, let's try to first build upon bankable CSP technology, in this case being molten salt tower, and try to demonstrate for the first time in Europe a megawatt scale supercritical CO2 cycle that would run using conventional solar salts. And the reason for that, and this is from another paper, but it's okay, we have very ambitions in the sense of being the first in Europe to do that, to do it in a real operating conditions, as you will see next. And the reason is that already at the temperatures at which we could operate a cycle using molten salts, we see that even in simple configurations of the cycle, like you could see here in this paper from Craig Tershi, we can attain good efficiencies or comparable efficiencies to what you will attain with steam cycles, but at the same time perhaps enabling more modular or smaller systems, which can make it more financially possible. Like Stefano showed, then our project vision, and like I was mentioning, is that by demonstrating the components that are in the circle, and you will see that we're building a purposely, designing a purposely built pilot plant where actually these components in the circle interact, as you will see next. But our idea is that by demonstrating these components in the circle, namely the molten salt electrical heater, the primary heater, all the turbo machinery and main heaters in the power cycle, then we can enable a system like the one I'm showing in the future, where basically you have conventional, let's say molten salt tower here, molten salt tower, where you have salts being heated up, just like in Nord 3, which is one of the replication cases. But unlike, unlike using a steam cycle, we're trying to use a supercritical CO2. And the difference also is that in parallel to the tower, we can provide heat also by means of electrical heater if the solar radiation from the tower wouldn't be sufficient, or if we want to boost temperatures or maximize the flow because we have excess PV or so. So we want to try the different approaches in terms of from a flexibility point of view, what the electrical heater can offer when hybridizing with the PV more actively. So that towards the grid, the system can be more flexible on one hand because of the electrical heater, but also because the supercritical CO2 should be more flexible. And that's something also that we want to explore doing the tests. So in our timeline, how we see this, how do we get there? Well, at the moment, like I said, Stefano mentioned, the project started in 2020. So the first year, which just will be in a week from now, we have focused on component design, optimization, and towards prototyping, which will happen now in next year. And here I'm talking about the compressor design, the turbine design, the heaters design, and both the primary heater and the electrical heater, and the recuperator primarily. We will move on towards the actual prototyping and test before we do installation and final test campaign in 2024, where we expect to learn then how the system will operate and gain experience from it. And at the same time, we aim to end the project also with an upscale design optimization for a 10 megawatt system, where even though we're not going to demonstrate it, then just show how the systems or the components can be upscaled and what are the limitations then. As we see it, like Stefano mentioned also in his slides, we think that should the project be successful and we can show that the cycle actually is viable and is able to operate at the temperatures that we're handling now. One thing I should say, by the way, is that as you will hear from Franco Tosi Mechanica later, the turbine, even though we are operating the system at the turbine in the temperature is roughly 585 degrees, the turbine is actually designed to handle higher temperatures. So we are actually thinking of moving even beyond the state of the art, should in terms of design at least. Anyways, as we see it is after the project, we will set the path for upscaling. Hopefully by our partners in the project, they can uptake the results and push market entry of the solution. And finally, such that by 2030 we can have a commercial molten salt driven supercritical CO2 plant, possibly hybridized with PV. I'll focus here on supercritical CO2, but I should say that one of the key outcomes from this project as well is that the actual demonstration and of the molten salt electrical heater, which might as well not be used for supercritical CO2 applications later on, can also be used directly even sooner than 2030 for other commercial purposes, being an economic battery or so. Later on, we see that in the project, we also are going to carry in work package 1 the analysis of more advanced hybrid CSP PV layouts, where the temperatures are 700 degrees Celsius or more, so not relying on molten salt. So I'll talk about the pre-engineering work and the work package 1 work, which is the one work package we lead at KTH. So that work package has a twofold objective. On one hand is to develop simulation tools that enable us to assess the economic feasibility of this, the different layouts we're assessing. So not only the replication one that I showed before, but also the, let's say, the future hybrid ones as we see it. And the second objective, and probably of more interest for now, for most of you attending, is actually to carry all the pre-engineering work that deals with the demonstration side itself, the pilot. So how the pilot should look like, what are the components we need, what is the balance of plant we need, how the tests are going to look like, such that we set the path for the work package 6 work, which is where actual engineering happens and procurement starts, which I should say actually already started. The work package is on track on the hand, and I can say, I mean, that's what this table shows. So we have a number of tasks. Some already actually are completed. The first one, where we look into defining the layouts that we're going to look into this project, not only the molten salt one, but the other hybrid ones. Task 1.2, which is led by Abengoa, it's dealing with all these actual engineering And there we it was very active this year, since we had to close down the actual cycle configuration and well, all the thermodynamic and boundary conditions for our system, and start thinking on defining the actual demo, as you will see next. And then task 1.3 and 1.4 relate to the actual modeling aspects. So 1.3 considers all the key performance indicators. What are we going to look into? How we're going to assess whether this is something that is techno-economically viable or not. Not only the demo one, but also the, let's say, advanced hybrid layouts. And the modeling part is ongoing and will continue so until year 3. So when we started looking into this, I'll show some pre-feasibility of like why we thought this concept would be interesting, regardless, even if it's not the highest temperature, the more, let's say, most of the potential you can get out of supercritical CO2 system. It's that we thought that already, operating a cycle at 585 degrees with molten salts, meaning 565 degrees with molten salts, was already competitive. So our preliminary techno-economic analysis showed mainly two things. One is that that already at 25 megawatt level or so, which is what I'm trying to show here on the top right graph, we see cost competitive values of LCOE. This, by the way, for a location in typical conditions, Southern European. So this was made for Seville. We're using Africana as a basis. And we see that, okay, that the case improves as we scale up the cycle, of course. Which actually, it's good on one hand, for those that have been in the industry, they know that most of these CSP projects are viable only because they are very big in scale, which at the same time brings another challenge, which is actually reaching financial closure. So we thought, okay, if we can enable a system that in the short term can bring to more smaller scale CSP, then this could be something of interest. And at these cost levels, then it would be of interest for sure. But we also look at let's say, an upscale system of 50 megawatt or so, where we're targeting a capacity factor of 70% at least. And we see that, or even for a Southern European location, we can reach values below 70 euro per megawatt hour. And of course, we try to assess this also in better locations like in Chile or Namibia, where this will be by far more competitive, right? So many assumptions here. One on the lane, one critical one is how the efficiency of the cycle and on the design of it and how it will actually work, right? And therefore, that's why we want to test this project. So we want to put this and see, well, even if in the simple configuration, this is not a simple configuration, would the turbine work? Would the compressor work? How can we control it? How can we put a system, and test it under the startup, ramp-ups, ramp-down conditions? So that led us to our demo. So I just want to show where the demo is. So you see on the right is the map of Spain. The demonstration plan will take place in Andalusia in southern Spain. And it's actually in between two power plants that are commercial and operating. So on the left here, as you can see, it's a 50 megawatt CSP plant called Africana. And on the right, you have a PV plant of 6 megawatt dual axis tracking PV plant. And for us, that's very strategic because we actually are talking about hybridizing PV with CSP. So even though we're not going to be, directly in either of, we are going to be using similar infrastructure. So our grid connection point and utilities within possible. This is the schematics of the preliminary demo layout as we have foreseen it. We're trying to be, this is actually a work mainly carried by Abengoa, which I think are also in the call with us. But what you see here is a first rough schematic of how we see our pilot plan. And I should say this is an independent pilot, as you can see on the right, which is maybe easier than the PNID. What we try to do is have a small loop of molten salts where we have our single buffer tank. And this tank, it's being heated up with electricity that comes from the salts are being heated up by electricity that comes from the grid, basically. And we have a 6 megawatt electric, approximately, inline heater that actually provides the heat, so that then we keep our salts stored in this buffer tank. Once stored, or even during operation, I mean, this buffer is actually not intended to be a Carnot battery itself, but more like just for provide stability to our project. For the operation. Well, once stored or once hot, well, we also provide heat to the primary heater, and we can do it continuously in line with the electrical heater or just from the buffer tank. And this primary heater then is just molten salt to supercritical CO2 heater, where the design conditions of the turbine are 565 degrees Celsius and 186 bar approximately. In the system, in the cycle itself, I can say this is just the simplest configuration, which is the one we want to try, including the recuperation. And so therefore, the main components I can highlight that are being developed in this project are the primary heater, the turbine, as you will hear later from Franco Tossi, the compressor from Baker Hughes, and the heat exchangers, so both of them from Lointec. And we also want to try, of course, a wet surface air cooler, which we are still in the discussion. Overall, the system will have roughly a 2 megawatt gross capacity, and net 1.4 is our target. If you do the math, I mean, 6 megawatt electric and 1.4 net, you understand that our pilot should target roughly just below 25% efficiency, thermal efficiency. Now, if I move to the PNID on the left, what we're trying to do is to optimize our area and to condense, let's say, if you see on this block here, these are all our hot loop, these are all the molten salt loop, to have the turbine and the compressor, which we're not going to be in the same axis, in the area of CO2, we call it, and then, well, our cooler here. So we have a recuperator here, the turbine, the compressor, and then all of these other systems are basically our auxiliary systems and the control house. This is a bit of what I said. Maybe I should have used this, where in the blue you have all the CO2 related components, and in orange the hot part with the molten salt. In terms of tests, we are aiming for 500 hours test minimum, under which we're going to try to operate the system in 2024, by the way. And there are different operating modes, highlighting here maybe the startup routines, 2 standby modes where we are talking about a cold and a hot standby. And during normal operation, we want to test different loads or hard test the system by imposing different ramps and see how it actually reacts. When it comes to the future advanced layouts I was mentioning earlier, well, we're thinking, of course, we're following very well what's happening in the CSP community and in the SolarPACES in general. So even though our project aims to demonstrate primarily molten salt to supercritical CO2 system, we are assessing from a techno-economic point of view and modeling simulation point of view, hybridization of a particle plus PV system or an air-based plus PV system. And in this context, I will invite you to follow 2 presentations. So I think it's on session Thursday 1C, where my PhD student, Salvatore Guccione, will be presenting part of his work. At the same time, we have recently published, by the end of the last year, a techno-economic analysis of the system, as you see on the right, non-hybridized, but moving forward, we want to assess them hybridized with PV. We're looking also next into more of the liquid path as well, but we just started with the ones I showed earlier. And the liquid path, just as the generation 3 CSP, we want to assess at least the chloride salts and sodium chloride salts hybridized with PV, and see where they end in terms of techno-economic analysis and, from a comparative point of view to the one-side system we're demonstrating. So to summarize, to wrap up my part, I think our main driver here is that there are many opportunities for enhancing cost competitiveness of CSP, as you will hear this week, I'd imagine. One key one, it's shifting to supercritical CO2s. What we thought was, okay, even though this is a key one because they enable higher temperatures and therefore higher efficiencies and compactness, etc. The solar collection part is not yet demonstrated, so let's start this project just to try to de-risk the supercritical CO2 part. And therefore, that's why we say this is a step towards commercial hybrid PV CSP, starting with molten salt as the bankable CSP solution that we know today. The project aims to have a 2 megawatt demo plant that will be running in 2024 for at least 500 hours in the premises of La Africana in Spain. It's 4 years. We have only been through the first one, just getting there. Like Stefano mentioned, it's an industry-driven consortium, since most of the partners are industry, where Stefano's team in Drina Consulting are leading it, and KTH supporting on the scientific coordination. We will test and publish results from megawatt scale components that are designed and their performance, and we will assess different layouts, and we're open to collaborating in doing so. So thank you very much. And should you have questions, of course, you can email me directly here as well, or contact me. I'll be attending the conference through the whole week.
Thank you very much, Rafael, for your presentation. We already have the first question addressed to you. However, I would like to gather all the questions and devote the last part of our event today for addressing all the questions raised during the presentations. Thank you very much. And I would like to invite now the next speaker, Simone Maccarini, to introduce us to the supercritical carbon dioxide cycle and turbo machinery in the Solar School demo.
Thank you, Constantino. I'm sharing my screen. Can you see my screen? Hopefully, yes.
Yes, yes.
Okay, thank you very much. So, okay, I'm here to present a cycle introduction of the demo cycle and some of the design analysis performed by us. I am Simone Maccarini. I am a PhD student at the University of Genova. And the University of Genova scope in the project is to basically in the first part to select the demo cycle operating points. So together with the partners, we agreed on this configuration with a simple recuperated supercritical CO2 cycle, a very simple configuration with thermodynamic values you can see in the table on the left. And to test on the demonstration site with an upscaled configuration that we foresee to reach well above 30% of total efficiency. And starting from these, we selected different control loops and the main degree of freedom of this cycle, which are of course the heat power entering into the cycle, the total mass in the loop through which we want to control the cycle, and of course the mass flow rate of CO2 flowing into the cycle. We decided so to control these main parameters through different actuators and with them perform some of the very first of design analysis. So we selected the mass flow rate of the molten salt, the variation of the total mass inside the cycle, and to control the mass flow rate, we selected to vary the values of the compressor bypass valve, or alternative to evaluate the result at different compressor speed. So basically, I want to show you some very basic results from these analyses. So here is the variation of the turbine inlet temperature varying. So basically, at a mass variation of the cycle at 0%, so with the constant mass inside the cycle, we can of course see that there is a decrease in the turbine inlet temperature, which is strongly affects the behavior of the whole cycle. And on the left side, you can see the variation of the opening of the fractional opening of the compressor bypass valve, and on the right side, the variation of the compressor speed. Of course, all is dimensionalized on design values. So using the pre-designed values of all the components given from the partners, these are the first main results. And what is the consequence also of this, of the behavior of the TIT and of the whole cycle, is that we have, of course, a decrease of the efficiency with the power load, but we have a better behavior with a variation of the compressor speed. And so now we are performing a different combination of these two strategies to allow different operating points of the demo cycle. So this was just a brief review of the very first analysis conducted by us, and I will leave the floor to Beckeriggs. Thank you.
Good afternoon to everybody. Thank you, Simone. I'm working as system engineer in Baker Hughes in the centrifugal compressor department following new project introduction. And I'm specifically the system engineer for the solar SCO2 project. If you can move on the next slide, please. So for solar project, Baker Hughes' scope of supply is the compressor design, production, and testing. The activities, as already said by the other partners, started almost 1 year ago. The first one for us, the first important one for us, was the definition of the inlet thermodynamic conditions. These inlet conditions are quite close to the supercritical to the CO2 critical point and are very important to guarantee compressor stability and operability. After that, we started the conceptual design of the compressor for the demo plant that was completed in March this year. And the results of this conceptual design was basically a 3-stage centrifugal compressor with a VFD motor as driver that was defined based also and leveraging on the experience that Baker Hughes gained working on the STEP and SCO2 flex programs. It is really interesting to highlight the fact that the supercritical CO2 has a very high density, and this high density is providing, is giving as a result machine that has a very high power density, but very small machines. So at the same time, we can have a benefit, so the reduction of the footprint of the machines, of the weight of the machines, and at the same time, a challenge because the small dimension of the machine can be a problem of manufacturability. So all these aspects have to be taken in account starting from the first design phase, from the conceptual phase, including the manufacturing in all the design phases of the project. In addition to this, Baker Hughes is also the owner of 2 tasks. One is the integration of the compressor and turbine on the same shaft line, and the second one is the providing guidelines for the compressor upscale. So starting from the compressor designed for the demo plant, we have to provide guidelines for considering bigger size of compressor. If you can move on the next slide. Here are indicated all the activities ongoing. Basically, at this stage, we are doing the preliminary design phase of the compressor that is due to end in almost 1 month time. And after that, we can release the drawing to buy the raw material for the compressor. Here is also reported the preliminary cross-section that is under finalization of the compressor, where are highlighted in red the main dimension of this machine. As I said before, we are talking about a very small machine. So the inlet flange and the outlet flange are respectively 3 inches and 2.5 inches, while the barrel casing of the machine has a almost 800 millimeter diameter and a length of around 674 millimeter. So this is just to give you an idea of what we are talking about. At this stage, we are also evaluating carefully the internal leakages of the compressor because in correlation with the small dimension of this machine, those leakages that for our standard compressor are less important, here becomes very crucial, because they can affect in a very important way the efficiency of the machine. So those are under deeply evaluation, and we are also trying to figure out what mitigation action, what action can be carried out to reduce this. The expected end of this analysis is by the final detailed design of the compressor that is due by almost June next year. Now we are, sorry if you can come back very briefly, I will summarize. We are also in the design phase of the first impeller, suction plenum, and discharge scroll. Especially for the first impeller, I want to highlight that the design of this impeller is specific, taking in account the characteristic, the thermodynamic characteristic of the supercritical CO2. So this design is carried out ad hoc for this machine. In addition, we have we are ready with a compressor performance curve. Simone, if you can move, please. Thank you. The next activity that will involve our department and Baker Hughes are finalized for the delivery of the machine that is due by March 23, and are moving on different items. So we start in the next month the activity on the auxiliary systems, because we have to provide the loop oil system and the seal gas system for the dry gas seal of the compressor, and we have the intention to review our requirements for those systems that are mainly based for oil and gas application, and we want to relax them, considering that this is a supercritical CO2 application where there is no risk of ignition of explosive or explosion. As I said before, the compressor raw material are due to be purchased before the end of this year. The drawings are expected to be issued in November, and after that, those material will be purchased. And we are expecting to finalize the compressor design, so completing the optimization of the aerodynamic components. First impeller will be studied with an high fidelity CFD in actual design condition. As said before, we are planning to finalize the analysis on the compressor leakage. We will assess the rotordynamic behavior of the compressor in the final configuration of the machine, and also the operability in off-design condition, and provide to all the partners the compressor performance map. The machine of the compressor, the manufacturing of the compressor, is due to start later on next year and be completed by end of next year, in order to test the compressor and assembly on the base plate and ship to site. Thank you. I have completed my presentation. I pass the ball to the next one, that is Emanuele Pesatori.
So thank you. I'm Emanuele Pesatori, and I'm the head of product development of Franco Tosi Meccanica. Franco Tosi Meccanica is in charge of Simone, please, can you move on? Thank you. Is in charge of the work package 3. That means to develop the feasibility study, the design, the upscaling assessment, and the manufacturing of the supercritical CO2 turbine to be applied in the power loop of the SOLARSCO2OL project. This is a turbine that has a power of approximately 2 MW. This is indeed a small power for a supercritical CO2 turbine, but is good for to provide good reference for next commercial plan. So up to date, the feasibility study of the turbine has been concluded and delivered. Now we are in the phase of the turbine pre-design and material pre-selection. So the turbine configuration has been selected, confirming the first assumption we have made. Beside the temperature that is in any case almost high, that we have to apply for the solar school, we have the aim to study the possibility to apply this kind of machine up to 650 Celsius degrees. And so we need also characterization, at least under creep point of view, of different material. Taking some material as a reference and exploring the possible selection of nickel alloys such as N18 and so on, and new material as the AF955 or the N09955. Then the turbine finalization of the design finalization will take place basing on also on the in-home design developed tools that are mainly 1D thermofluidodynamic design codes, where you see some parts of the user interface of this tool in the in the first release. We take advantage of in the feasibility study. After the turbine design phase, it will take place the turbine manufacturing with the power loop integration, with the test that we have to perform and the trial operation within the fourth year of the project. Simone can move on, please. Thank you. So the configuration we have assessed as feasible is a radial plus axial one that allow us to contain the power density within acceptable limits. So supercritical CO2 has the characteristic to bring the power density of the machinery to really high levels that are not faced during typical steam and gas turbine design and operation. This can drive to huge stability, aerodynamic stability issues, and it's important to assess the safety margin by this stability. Obviously, some specific methods has to be established, since usual norms and criteria are not featured for this kind of machines. Then the extremely small size of this machinery bring us to handle with the internal thermal gradients and shaft seals that are typically Draeger seals, thermal operating condition that can be extremely severe. Besides this, it's mandatory to achieve acceptable blade path size for gain sufficient volumetric efficiency and scalability to avoid having to design next commercial machinery in a completely different way from what we have done for this. And so the results, our approach, and a reasonable approach, is to divide the machine in two sections. You see some fluidodynamic study made with CFX, giving us an idea of the design we have achieved. So a first section that is a radial one and two axial stages. What is pretty interesting is that with the CO2 and supercritical CO2 particularly, we can achieve interesting high level of Mach number, even if the load, the enthalpy drop is not that much high. This allows to achieve interesting feature and figure for the expansion efficiency. You see that we can easily stay in a favorable range of Mach number that is in the range of 0.3 to 0.6. So the last figure on the right give us a measure of the possible volumetric and secondary losses that we can experience when the size of the machine is reducing in this way. Simone, please, can you move on? Okay, thank you very much. So here we have a sort of miscellanea of the achievements and the say the track we have established to get to the final design of the machine. The gray, say the steel color figure is the is what can be close to the final configuration. You see that the radial impeller that is the first stage of the turbine, followed by the two axial ones. The overall dimension are very small. You see on the right, you see 6 millimeter, 18 millimeter, almost say 20 millimeter of last stage blade height, with a possible and a preliminary configuration of the sectional drawing of the machine, with particular attention and devices to separate the hot section of the machine from the shaft end seals one, to provide dedicated cooling device. Concluding, the preliminary bladed path and the overall turbine configuration is almost defined. Obviously, final design must modify in a reasonable way these achievements. What will be needed is also a main turbine parts material creep assessment to address the design up to higher temperature level. And one of the most important next step will be the integration in the power loop, in the demonstration power loop, for which non-dimension operating curve will be has been already provided and will be enhanced in precision and suitability for the plant and for the simulation of the transient of it. So this is almost all. Thank you very much. You can find our contacts. Don't hesitate to contact us for any kind of information, even curiosity and suggestion, obviously. And thank you for your attention.
Thank you very much, the three presenters, Simone, Alberto, and Manuel, for their joint technical presentation on turbo machinery. I would like to remind you that all the attendees can submit their questions in the Q&A button at the bottom of their screen. So far, I would like to thank also Rafael that has been answering all the answers submitted so far. And now we may proceed to the next presentation about the heat exchangers and molten salt electric heaters. And I would like to invite Alvaro Bilbao to share his screen.
There we go. So Okay, should be on now. Hello, everyone. So this is the presentation about the heat exchangers manufactured both by Lointec and by SECO for the Solar School project. So my name is Álvaro Bilbao, and I work for the energy division here at Lointec. If you allow me, I will just make a brief introduction about the company. We are a family-owned company specialized in the design and manufacturing of heavy equipment that go from reactors and columns to industrial boilers, and especially to heat exchangers for the CSP sector. Within the CSP sector, we do not only design and manufacture the heat exchangers, but we are also specialized in the developing of turnkey solutions for steam generation systems, both in concentrated tower and parabolic throw plants, and also for the thermal energy storage systems in parabolic plants as well. We've been working over 20 years in the CSP sectors, pretty much since it started here in Europe. And we've both designed and manufactured over 800 shell and tube heat exchangers for around 50 CSP plants all over the world. So, so how does our experience here in the CSP sector help us to accept the solar school challenge? So for this project, we are going to be the WP4 package leaders. This package is focused on the heat exchanger design, prototyping, and integration in the plant. Not only the shell and tube heat exchangers, but also the electrical heater, which in this case will be both designed and manufactured by SECO. SECO will explain the specifics of this equipment on the next slides. So as our colleagues have explained so far, this Brighton recuperative cycle employs a recuperator, of course, CO2. And then we have the primary heater, which is the molten salt 2 CO2 heat exchanger. And you can see both units in the layout of the plant and how they are connected in this Brighton cycle. So our role in the Solar School project, it will be, of course, to first numerically and experimentally study the shell and tube heat exchangers along with the electrical heater for SECO in this case. And our ultimate goal will be to, as explained before, to upscale these proven prototypes. So hopefully we can implement them in both solar or non-solar power contexts. In this case, the CO2 is a new fluid for us. It will be the first time that we'll both design and operate in supercritical conditions. Furthermore, we are also combining the CO2 in the case of the main heater with the molten salts. This is a tricky fluid, very viscous, and with a very high temperature, freezing temperature fluid. These salts freeze around 260 degrees. So it will be a challenge to combine these two fluids in the shell and tube heat exchanger. So for both heat exchangers manufactured here at Lointec, both the main heater and the recuperator, the employed design will be the hairpin design. This unit, it's a very versatile heat exchanger made for high temperature differences during operating conditions. In this case, these units will work at very different delta T's. In the case of the recuperator, we have around a 350-degree temperature drop. In the case of the heater, as we said before, it's around 200 degrees. So this design is the optimum choice to avoid thermal shocks, thermal stresses within the units. As it is as the hairpin design is divided in two legs, there is pure counter current heat exchange within the unit. As most of the shell and tube heat exchangers, we also have an easy channel access for maintenance and reparation purposes if needed. For the heat exchanger design, we have combined both commercial software such as HTRA and also in-house tools. At the end, our experience in the design and performance of heat exchangers throughout the years has helped us to develop specific add-ins to already existing commercial software. You can see some screenshots here from the designing stage, preliminary design stage in this case. So currently, as we have already finished the initial conceptual design of the shell and tube heat exchangers, we are now focusing on the computational fluid dynamics simulation stage. For this, our research and development partners, Eagerland, RINA, and the Third Institute, are building geometries to model both the molten salts, building the geometries of the heat exchangers, and later simulate the molten salt and sCO2 fluids inside these units. This is a big task group that where manufacturers and R&D partners work together. So we expect to confirm the expected behavior of this fluid inside the heat exchangers as it was modeled during the initial stage, while we try to seek any optimization possible, if possible, as I said, when seeing the flow distribution and the heat exchange once it has been pictured in the CFD. So we hope to finish this stage by the end of this year, so we can start the manufacturing process and stage at the beginning of 2022. This is just a few recap of the heat exchangers, shell and tube heat exchangers, and now I would like to leave the floor to our colleagues from SEICO to explain the specifics about the electrical heater.
Hi, Alvaro. I'll take over. I think James not with us, so he couldn't join us, I guess. So I can bring the slides.
Thank you for this, Rafael.
Oh, thank you, Rafael.
Okay, so I'll present this on behalf of SEICO. So SEICO is a partner in the project, and they're actually a German-based company, which is part of a larger group, which is the Exit Group. And well, the technical manager in the project is James Brown, who couldn't join us. So, like I said, well, he had this slide about SEICO, but I already mentioned it. SEICO is relatively, still is family-owned, but it's relatively all over the place. So they have 311 staff based in 5 countries, where they are based on one in Asia, one in the US, and one in Europe, and so on. And they handle different, from those offices, basically they handle or tackle all different multiple countries. So 147 countries they have worked in. So it's a relatively, for being a provider of electrical heaters, I think it's a relatively large company, and it was many years of experience. And they got interested in this project, and mainly because, I mean, from what I know, it's they've been starting to get a lot of requests for electrical heaters for thermal battery applications. So not only for molten salts, but for others. So this felt fit very well in line with their current business. And even though they've been many years in the business, what they realize is that the supply of a conventional heater is not the same as, if it's to be purposely designed for molten salts. And we talk a lot about it on some of the slides, but basically, like I said, the main project is to develop their own, or why they joined in this is to understand better molten salts in general, and to be able to come with solutions off the shelf that they can provide for future projects, and not only in the context of solar thermal applications, but others. How does the heater look like? I think it's here's our presentation. So in principle, we know the size will be somewhere around 6 to 7 megawatt. I think 6.8. And you see here the medium voltage, high voltage, or 690 volts. Basically, it's a baffled heat exchanger type you could think of. It's where you have your inlets and outlets, similar to what Albert was describing earlier, but now instead we have no fluid passing through the baffles, but the bundle is actually an array of element tubes, basically, which are resistances, and these are controlled in different ways. That could be part of the design. So whether we control them, how we control the temperature in the longitudinal or transversely, or I mean, like on top or bottom, which temperatures we operate at, or target in the element, or even at the inlet or outlet, should we can keep the same temperature or so forth. Another big challenge for this is how we design this baffles and so on. So this is a standard configuration of an inline heater, and that's our basis for this project, but we have iterated already in different designs, as you will see in the next slide, since we've realized that a number of challenges will come with molten salts. And these challenges, I mean, well, first of all, it's a closed loop system that can lead to a lot of hotspots. And these hotspots we see, of course, clearly a very fast degradation. I mean, if you have elements that are kept at 600 degrees Celsius or more, and you have a hotspot around it, then that immediately will lead to corrosion of the heater element, but also degradation of the salts, etc. At the same time, they need to be designed very carefully, such that we avoid solidification if we need to drain it, and that we don't have any, basically, well, any molten salt retained in the heater in such situation. Like I said, besides the actual geometry, which is part of the optimization, the other big thing in the optimization, it's the actual control. So we're assessing different CFD studies to understand how the elements should be controlling or regulating the temperature, and how to regulate also different stages within the heater, such that we control temperatures there as well. And this part of the control aspects for the heater are also being within the scope of Exit, even though, of course, in the project we have our key controller partners, which are, like Simone mentioned, Unige, together with Mass Europe, which will be the actual instrumentation provider or the control system provider. We are looking into, as part of optimization, into different type of elements. So in the past, I mean, under the first design, I mean, we have tried a length like that is shown here on top, but right now we're moving towards more sort of bare naked elements, if possible, and simpler elements, and that is part of the design right now. So it's part of the choice or understanding what is better in this for this particular application. Like I said, one of the first in this first year, one of the first things we realized is that how do we enhance turbulence inside to keep relevant flow through it and relevant velocities. And we realized that under standard configuration of baffles, we might face issues of buoyancy with the salts, and we're going through that optimization. So therefore, we might increase the complexity of the baffles, as you can see on the right. We might assess different ones. And again, this is an example, not exactly the one we're going to use in the project, but we are thinking of different solutions in that sense. And the reason why, and I think, well, yeah, we decided not to show it here, but it's, to avoid this depending on the flow, I think this is actually not of like molten salts. These results that are showing here by exit, but depending on the flow, what we have observed is, depending on the fluid, what we have observed is that actually we do see formation of large areas of hotspots with the molten salts with a standard configuration. At the same time, we see that there is that the design where initially pursued could lead to stratification, which is undesirable. So we are increasing the complexity, we are playing with the control aspects, etc. And we aim to have an optimized design purposely made for this application already within March next year, which is our month 18. In conclusion, we've seen that, okay, our first, let's say, off-the-shelf heater tested for molten salts would actually lead to many troubles. So we're optimizing it in different ways. So handling temperature control, also handling heat flux from the elements throughout the whole distribution and different stages, and increasing turbulence or playing with the geometry in terms to actually avoid stratification when possible. Okay, thank you. I just wanted to briefly talk about our efforts on the molten cylindrical heater, and I see there are some questions.
Thank you, Rafael, for taking over the presentation. If we have any other questions, we still have time to answer them. So far, Rafael answered in written the questions raised in the Q&A section. So as
well,
far
actually,
as
sorry. I see James is actually here with us. It's just that he's in the present in the attendees, so he couldn't join us panelists.
Okay.
So
Well, if there are no other questions, please be reminded that you have the contact information of all presenters. You can contact directly and ask any possible questions raised after the presentations. The recording will be, and the presentations will be available online, probably next week. And I would like to, after thanking all the presenters and the attendees, I would like to invite Stefano Barberis to make a closing statement of our event.
Okay. There is in the meanwhile a question related to presence of hotspot in the electrical heater. Actually, this was one of the key topics we discussed 2 weeks ago in Sevilla, because let's say we are practically looking at starting from some simulations we performed, CFD simulations. We saw that there are some hotspots in the electrical heater, and such hotspots are also changing depending on the orientation or how, let's say, we will install the electrical heater in the power plant. So let me say, this is something that we are currently investigating. So I hope that in the next seminar, we will be able to provide you more clear answer. So generally speaking, let me thank all the speakers that have participated so far in this workshop. I would like to remind all of you to participate during SolarPACES in the conference session where KTH, for example, is presenting the first preliminary results related to the techno-economic studies of solar coming from Work Package 1 of Solar School. And to all of you, I would like to thank you again for attending. And at the same time, also I would like to ask to all of you to follow us on our project website, our social media. And last but not least, a big thank to Konstantinos and to Estela for organizing this event. I hope all of you enjoyed it, and let's say, follow us and keep, let's say, the eyes open on the potential of supercritical CO2 as the perfect match for CSP.
Thank you very much, Stefano, for your kind words. I would like to thank everyone for joining us today.
Thank you again. Have a nice afternoon and evening for the European one.
Bye all.